Hello viewers, in today's session we are going to discuss another important and conceptual problem from limits, right? And here we have a very important problem in which the greatest integer function and the fractional part function are involved, right? So we'll utilize the definition of fractional part function and the greatest integer function to solve this problem, right? So here we are given this problem, that is, if the limit x tends to 1, cos of fractional part of x minus 1 divided by 1 plus lambda times tan inverse of greatest integer of x minus 1, if this limit exists, then we have to calculate the value of lambda, where lambda belongs to the set of real numbers, right? So we know that if the limit of a function exists, then the right hand limit and the left hand limit must exist, right? And moreover, the right hand limit and the left hand limit should be finite and equal to each other. So here in this problem, what we will do, we'll first find out the right hand limit and then left hand limit, and then we'll equate both the limits to form an equation in lambda, and then we can solve that equation to get the value of lambda. So let us start. So here we have x tends to 1, right? So in the real number line, if we take x is equal to 1, and when we calculate the right hand limit, then we approach towards x is equal to 1 from the right of x is equal to 1, and we reach at a point which is known as the right neighborhood of x is equal to 1, that is 1 plus h. And similarly, when we tend towards x is equal to 1 from the left of x is equal to 1, then we reach at a point which is known as the left neighborhood of x is equal to 1, and this point may be taken as 1 minus h. And remember, this quantity h is a positive quantity, and it is infinitesimally very small, and h lies between 0 and 1. So let us quickly see the definition of fractional part function. The fractional part of p is defined as the difference of p and the greatest integer of p. So this definition is going to be very useful while solving this problem, right? So the right hand limit, the notation for right hand limit is x tends to 1, and here we put a positive sign, and here we have f of x, where f of x is this function, right? So we'll take x is equal to 1 plus h, and when x tends to 1, then h tends to 0. So we can now transform this limit in terms of h. So we have limit h tends to 0, and we have f of x. X may be replaced by 1 plus h, right? So now we have limit h tends to 0, and we can replace all these x by 1 plus h in f of x. So we have cos fractional part of x minus 1, so we have 1 plus h minus 1 divided by 1 plus lambda, and here we have tan inverse of greatest integer of x minus 1. So we have 1 plus h minus 1. So let us simplify this expression. So here this one and this one get cancelled, and we have cos of fractional part of h. And in the denominator we have 1 plus lambda, and here also this one and this one get cancelled, and we are left with simply tan inverse of the greatest integer of h. So now, utilizing this definition of fractional part function, we can now write limit, then we have h tends to 0, and cos of h minus greatest integer of h. And in the denominator we have 1 plus lambda times tan inverse of greatest integer of h. right? Okay, so now we have to evaluate this limit and see whenever we come across with the greatest integer function, we cannot directly substitute h over here, right? So instead we'll make use of the definition of greatest integer function. So see, h is a positive quantity and h is infinitesimally very small, and h lies between 0 and 1. So the greatest integer of h should be equal to 0, because h lies between 0 and 1. So now taking the greatest integer of h is equal to 0 over here, we have limit h tends to 0, and we have cos h minus 0 divided by 1 plus lambda times tan inverse of 0, right? And see, tan inverse of 0 is equal to 0. And here we have now limit h tends to 0, and we have cos of h divided by 1 plus lambda times 0, because tan inverse 0 is 0. So now this term goes to 0, and we have 1 plus 0, that is simply 1. So we are left with only limit h tends to 0 cos of h. And when h tends to 0, then cos h tends to cos of 0, and cosine 0 is equal to 1, right? So the right hand limit of this function when x approaches to 1 is given by equal to 1. Now let us find out the left hand limit. So the notation for the left hand limit is the limit, here we have x tends to 1 negative, and here we have f of x, right? So now we can take x is equal to 1 minus h. When x tends to 1, then h tends to 0, right? So again rewriting this left hand limit in terms of h, we have limit h tends to 0, and here we have f of 1 minus h. Now f of 1 minus h can be written with the help of this expression by replacing x by 1 minus h. So we have limit h tends to 0. Here we have cos fractional part of 1 minus h minus 1, and then we have 1 plus lambda times tan inverse of greatest integer of 1 minus h minus 1, right? Okay, now simplifying this expression, we have cos. Now see, this one and this one get cancelled, and we are left with the fractional part of minus h. And here we have 1 plus lambda, and this is tan inverse. Here also 1 and minus 1 get cancelled, and we are left with greatest integer of minus h. So now to move further, what we will do, here we have a fractional part of minus h. So again, utilizing this definition, we can write the fractional part of minus h as minus h. Here p is minus h, so here we have greatest integer of minus h, right? So now we have to take care of this term, that is greatest integer of minus h, which also appears in the denominator, right? Now see, h lies between 0 and 1. So if we multiply this inequality throughout by minus 1, we have 0. The direction of the inequality get reversed, and we can rewrite this inequality as minus 1, then we have minus h, then we have 0. So this important inequality suggests that minus h lies between minus 1 and 0. So the greatest integer of minus h should be equal to minus 1, right? So substituting the greatest integer of minus h over here, the fractional part of minus h is minus h minus, then we have here minus 1. So this is minus h plus 1, right? and the value of greatest integer of minus h is -1. So now this limit is equal to limit h tends to 0, and here we have cos of 1 minus h. This is minus h plus 1, so we can also write it as minus h plus 1, and here we have 1 plus lambda times tan inverse of -1, right? Okay, so now when h tends to 0, we have cos, then here we have -0. We can take h is equal to 0, and here we have 1, and we have 1 plus lambda times tan inverse of -1, which can also be written as minus tan inverse of 1, right? Utilizing the result, that is tan inverse of minus theta is minus tan inverse theta from inverse trigonometric functions. So now this limit is equal to, here we have simply cos of 1, and here we have 1 plus lambda times minus pi by 4, because tan inverse of 1 is equal to pi over 4, that is 45 degrees. So this is cos 1 divided by 1 minus lambda pi over 4. So the left hand limit of this function when x approaches to 1 is cos of 1 divided by 1 minus lambda pi over 4. So now we have obtained the value of right hand limit and left hand limit. So equating these two limits, for the existence of this limit, we have 1 is equal to cos of 1 divided by 1 minus lambda pi over 4, because the right hand limit is equal to left hand limit for the existence of this limit. So now we can solve this equation. So taking 1 minus lambda pi over 4 to the left hand side, we have 1 minus lambda pi over 4 is equal to cos of 1. So rearranging the terms, we have 1 minus cos of 1 is equal to lambda pi over 4. And now making use of some trigonometry, see, cos of 2 theta can be written as 1 minus 2 sine square theta, right? Now replacing theta by theta over 2. So we have here cos 2 times theta over 2, 1 minus 2 sine square theta over 2. So now this 2 and this 2 get cancelled. So we have cos theta is equal to 1 minus 2 sine square theta over 2. So 2 sine square theta over 2 is equal to 1 minus cos of theta, right? Now taking theta is equal to 1 radians, we have 2 sine square 1 over 2, taking theta is equal to 1. So we have 1 minus cos of 1, right? So replacing 1 minus cos of 1 by this term, that is 2 sine square half. So here we have 2 sine square half, and here we have lambda pi over 4, right? So we can also write this equation as lambda is equal to 4 times 2, that is 8, and dividing 8 by this pi, we have 8 over pi sine square half, right? So this is the required value of lambda for which the limit of this function when x approaches to 1 exists. So viewers, this is how, by making use of all these concepts, we can solve these kind of problems very easily, and the value of lambda in this case is given by 8 over pi sine square 1 over 2, where lambda is obviously, it belongs to the set of real numbers.